So in this video, we're going to look at finding the area bounded by curves when the curves intersect in three places. So this example says find the area bounded by the curves f of x equals x minus 1 cubed and g of x equals x minus 1. So a picture of the situation is shown here. And what we want to recognize is that the curves intersect in three spots: here, here, and here. So the area that we want to find, if we're finding the area bounded by the curves, is the sum of these two areas. And we're going to take two approaches to this. So sometimes you can use symmetry to simplify a calculation, and if you can use symmetry, you typically do want to use symmetry, but you need to make some sort of argument that symmetry can be used. So first I'm going to solve this assuming that I can't use symmetry so that we could see how we would need to lay that out. And then we will do the same calculation or the same area setup using symmetry to lessen the amount of work that needs to be done. So I've got three intersections. So that's the first thing I want to notice. The second thing I want to notice is that if I did representative rectangles that are vertical, I'd have dx slices, and here the cubing function is the function above, and then when we get past this intersection, the linear function is the function above. So if I make a representative rectangle here, the function above is different than for right here. So this tells me, because the function above switches when I get over this intersection, it tells me that I would need to break things into two integrals. And then I'm going to need, of course, to know these intersections. Now, graphically, it's easy to find those intersections just by inspection, but that's on purpose. That is to give us a check on our work. In general, if you can calculate the intersection, you're kind of expected to calculate the intersection. And then what we want to recognize is that the intersections occur when the two graphs are equal to each other. So if I wanted to calculate those intersections so I can set up my integrals, then I would take my cubing function and I would set it equal to my linear function. And then I would probably subtract my linear function from both sides. And then what I want to recognize is that x minus 1 is the same here and here, so I can factor an x minus 1 off. I want to avoid cubing this if I can. So factoring off an x minus 1, which shows up as a factor in each of these terms, that's going to leave behind an x. It's going to leave behind an x minus 1 squared here, minus a 1 right here. And then once I've broken it into a product of two functions, I can use the zero product property to separate those. So either x minus 1 is equal to 0, or x minus 1 squared minus 1 is equal to 0. So I can see x equals 1 as a possibility. And then I want to avoid squaring this out if I can. So I'm going to go x minus 1 squared equals, I'm going to add 1 to both sides. And then take the square root of both sides, which is going to give me plus or minus 1 sitting here. So we get x equals 1 plus or minus 1. So x is either going to be 1 minus 1 is 0, or x will equal 1 plus 1, which is 2. So I see that I get multiple values for x. I get x is equal to 0, 1, or 2. And then what I would have to do is come up with the y coordinates that go with these x coordinates. And probably the linear function would be the easier one to use. You have this y equals x minus 1 kind of guy sitting there. So just plug the numbers in. Plug in a 0, you get 0 minus 1 is negative 1. So we get the ordered pair 0, negative 1, which is showing up right here. 0, negative 1. There's that guy. And then y equals, plug in the 1, we get 1 minus 1 is 0. So when x is 1, y is 0 right here. And then plug in the 2, so we get y equals 2 minus 1 equals 1. So input 2, output 1. So finding those intersections wasn't particularly difficult in this case. So I'm going to erase this to give myself a little bit of room. So once I do that, it's just simply a matter of setting up two separate integrals. So first I'm going to run an integral from 0 to 1. So run an integral from 0 to 1. And then it's going to be the function above, which is the cubing function. So we're going to take the x minus 1 cubed and subtract the function below, which is the linear function x minus 1. And this will be a dx. And then we're going to add to that the area that we get between the two curves here. So plus, and then we're going to run that from 1 to 2 over the x-axis. And the function above now is the linear function, so it's going to be the x minus 1 minus, and the function below is the cubing function, x minus 1 cubed dx. So there's the integral setup to calculate the sum of those two areas bounded by the curves f of x and g of x. And I'm not going to integrate this. I don't think that this is a difficult integration. I know that you can do it. So let's just quickly talk about shortening the amount of work that we need to do by using symmetry. So we already calculated these intersections, so we don't need to do that again. This was 0, negative 1. This was 1, 0. And this one here is 2, 1. And it looks like the area here should be the same as the area here. And what we want to do is convince ourselves that that has to be true. And what we want to recognize is that each of these come from a specific toolbox function. So x minus 1 cubed is coming from the cubing function, and x minus 1 comes from the function y equals x. So x cubed and x, what we want to recognize from pre-calculus work is that both of these functions have odd symmetry. Odd symmetry. In other words, they are each function is a reflection of itself in the origin. So if you were to draw just the cubing function, x cubed, it's a reflection of itself in the origin. And y equals x is also a reflection of itself in the origin. So if we pretended for a minute that this is the y-axis, what we would have is two odd functions being reflected through the origin. And when we reflect through the origin, it changes our orientation, or we can see that it's the same as rotating 180 degrees. We could see a 180-degree rotation would carry this region into this region. So reflection through the origin gives you that you get the same result if you rotate by 180 degrees. So the idea is, because they're both odd functions, when you reflect through the origin, they'll lay over top of each other. And that tells us that this area is, by odd symmetry, exactly the same as this area here for the functions x cubed and x. So what you want to recognize next is that even though we don't have x cubed and x, we do just have a horizontal translation of x cubed 1 unit to the right, because there's the minus 1, and we have the translation of y equals x, 1 unit to the right because of the minus 1. So instead of having odd symmetry with respect to the origin like x cubed and x do, x minus 1 cubed and x minus 1 have odd symmetry with respect to the origin. The origin gets moved 1 to the right. It winds up at 1, 0. So we do have odd symmetry with respect to the point 1, 0. This region right here is exactly the reflection of this region through this point 1, 0 by odd symmetry. So indeed, it is perfectly acceptable because of odd symmetry. And what we want to do is recognize that it's odd symmetry that we're seeing, but it's perfectly acceptable by odd symmetry to say, hey, I'm just going to integrate from 0 to 1. And the upper function is the cubing function. So I'm going to take the x minus 1 cubed, and I'm going to subtract the linear function that's down below and multiply it all by dx. And then I want to recognize I have two regions of the same area by odd symmetry, so I'll double the result. Notice we could just as easily take the integral from 1 to 2 of now the upper function is the x minus 1, and we could subtract from that the x minus 1 cubed multiplied by dx and double that area. So instead of doubling this area, double this area here. But you can see that probably this is going to be more convenient, because having a 0 as a bound of integration is really nice when you plug it in for x. And having 1 as a bound of integration is going to be very nice as well. So these are probably easier bounds of integration to work with than 1 and 2.